Hello, students. I'm going to take you through a quick review of what you have already done, either between in class discussions or a whole lot of your work on your own, as far as supporting evidence for the Big Bang. And again, here is our standard that we're working from. So, construct an explanation of the Big Bang theory based on astronomical evidence of light spectra, motion of distant galaxies, and composition of matter in the universe. And so we're specifically going to be looking at redshift of light from the galaxies. We're going to be looking at cosmic microwave background um, as uh, as the remnant of the Big Bang, and talking about the redshift that happened in order to make that into microwave radiation. And then we're going to take a look at the composition of the universe. So let's go ahead and get started on that. So, definition for the Big Bang: it's the theory that all matter and energy in the universe was compressed into an extremely small volume that 13 to 15 billion years ago exploded and began expanding in all directions. Before the Big Bang, there was no time and no space. All the matter in the universe was compressed into an extremely small volume, and that destabilized and, for lack of a better word, exploded and began to expand outward in all directions. So I guess the technical term there would be that it destabilized, but for all intents and purposes, that would be that it exploded. And today we find that the universe is still expanding. So, when you are answering this part, your guiding questions will be: what is the Big Bang Theory? When did it occur? What was the universe like before? And what happened when the Big Bang occurred? And you can find all of those things right there in the discussion that we just had. Now, we're going to move on to what is the Doppler redshift. And so here is a visible light spectrum. That's the picture that I have up here, the graphic that I have up here. And so wavelengths that are emitted by objects moving away are shifted to lower frequencies and longer red lengths. And if we're just talking about the light spectrum, it's shifting toward this side over here. So it's going toward, as you're looking at the screen, it's going toward the right. Now you can have wavelengths here that shift way on over here into the infrared. And we're going to see how that happens here in just a little bit. Um, so when you're talking about this, you need to talk about the wavelengths as objects move away of shifting toward the lower frequencies and longer wavelengths. It's not technically correct to say that that light shifts toward the red end of the spectrum, because or it's not technically correct to say that electromagnetic radiation shifts toward the red end of the spectrum, because you can have radiation that's out here that shifts that way. And so technically that is not toward the red end of the spectrum. It is technically toward the longer wavelength end of the spectrum. Here's the red end of the spectrum, and it's not shifting that way. It's shifting away from it, shifting toward longer wavelengths and lower frequencies. So it's going to head that way. It's going to head to the right. It's going to head toward longer wavelengths, lower frequencies. If you have an object that's moving toward us, it's going to be shifting toward the left. So it's going to be shifting toward higher frequencies and smaller wavelengths. So you can see that the wavelength in nanometers, the wavelengths are getting smaller here, and you can see that the frequency is getting higher. And again, you can't really say that the electromagnetic radiation is shifting toward the blue end of the spectrum, because that's not technically true, because you could have um, ultraviolet radiation that is shifting on toward like gamma rays. And so you've got that shift occurring. It's to the left, and that is toward higher frequencies and shorter wavelengths. Okay, so please use the correct technical terms as you go through that. For galaxies outside our group, this redshift is known as Hubble expansion. Edwin Hubble did a whole lot of discovery about objects in space, motion in space, and he discovered this phenomenon in 1929. Now, here's something that's quite interesting. This is a pretty good graphic to show that. The further away an object moves, the more redshifting will occur. Okay, so if this is our reference, so this is our spectra for expected or known emissions of light. So this is an absorption spectra. So we're going to see little bands of light that's being absorbed as we look at this particular spectrum. And so I would need a reference here in front of me, but probably this is hydrogen and helium. And so if we take a look at the star right here, we're going to see that this star is reasonably close to us, not too far away. But we're going to see that those bands are all shifting toward longer wavelengths. Okay, so that's called a redshift, shifting toward longer wavelengths. But if we look at a nearby galaxy, not in the Milky Way, but look at another one, we're going to see, and obviously, so this would be farther away. We're going to say that the star was in our own galaxy. We're going to look at this other nearby galaxy here, and we're going to see that we have an even bigger shift, and you can follow these lines. So we got a line shifted over there, and then we've got a bigger shift here. So not only is it farther away from us, but it is moving farther away from us. We've got a distant galaxy, and you can see that there is a substantial shift. So we have this line that is all the way over here, and it's just about to go into the infrared. Okay. And then if we look at this very distant galaxy, all of the stuff that was down here super close to ultraviolet, it's all the way down here in like the green, almost moving toward yellow wavelengths of light. And we have this line that has shifted completely into infrared. And so you can see from this is support for that objects are moving away, and that they're like moving away faster and quite a bit. And if you think back to the balloon, and think about putting dots in different places on the balloon, if you have us moving in one direction and kind of another dot moving in another, then as that balloon expands, there's going to be great distances, and there's going to be kind of an increase in the expansion because you're moving in opposite directions. They're in different directions, not necessarily opposite, but different directions. Okay, so how is this redshifting evidence? So, according to the Big Bang Theory, after the Big Bang, the universe began expanding. It has expanded since that point and is still expanding today, and we see that in redshift. So, redshift supports that the universe is expanding and is still expanding. It has expanded in the past and it is continuing to expand. When we look at galaxies outside of ours, we can observe their shifts toward lower frequency end of the spectrum as wavelengths appear longer to us, longer and longer to us, as that galaxy moves farther and farther away from our galaxy. And so you're going to have these three guiding questions. The stuff that we just went through should have covered all of that. Next one, cosmic microwave background, cosmic background radiation. There are probably 5 or 6 different ways that you can say this, and they all mean the same thing. If you want to look up something on your own, this is that space-time from PBS Digital Studios. It is linked in one of our assignments. So this is a good way to look at this. So CMB is microwave radiation that is detected from all directions of the universe because it was formed from the light given off at the last minute. And so essentially what you had happening was, if you think back to the way that the video explained this, you kind of had these different flash bulbs going off. And as that was happening, you couldn't really see through the fog because we didn't have discrete atoms having formed yet. There was still too much plasma, it was still too hot, there was still too much energy. And so at the point where the universe neutralized, or where neutrons were able um, to form as part of as part of atoms, and before the charged particles were able to become neutral. So it got some electrons in there as well. So when that happened, the fog kind of cleared up. And so that one last flash of light that would have been going out in all different directions wasn't trapped any longer. It didn't have the fog to stop it. So that light could continue to travel. Well, the issue that happens with that is that over time, as the universe expands, that light was orange. So as the universe expands, that light redshifts, and it shifts all the way from the orange to the red color of light, and then it shifts into infrared, and then it keeps on shifting until it becomes microwaves. That's what we see now. Over time, could it move on toward radio waves? Very likely, very potentially, it could move that direction in a large number of years. So, cosmic microwave background accounts for the light or the electromagnetic radiation that was given off during the Big Bang and shortly after. And it is consistent with the idea that the universe was very hot and it was very dense a very long time ago, and that the universe has moved through or changed over time through different stages as it cooled. And so that's the idea of the red light, or sorry, the orange light redshifting all the way to microwave radiation as the universe continued to expand. Here are the guiding questions that you will need for that. And you have those guiding questions. And then we'll take a look last here at the composition of the universe. The early universe was extremely hot and dense, 10 billion Kelvin, and that was a little bit after the Big Bang occurred. It was actually hotter than that at the way beginning, and so this was hot plasma. So it had radiation and it had elementary particles. It was just a hot plasma, not someplace that any of us would particularly want to be. So during the expansion, the plasma cooled down, and it cooled down actually pretty quickly, but it cooled down at a steady pace. And so you started to be able to have the lightest elements that could come together in Big Bang nucleosynthesis. So temperatures in the early universe were high so that you could have fusion reactions take place, but they also had to be low enough so that fusion reactions could take place. So it's kind of like it had to hit that, uh, baby bear type thing of it's not too hot, it's not too cold, but it becomes to a temperature so that it doesn't stay in the plasma state, but you can actually still start to have fusion reactions. It takes a pretty high temperature for that to occur, lots of energy for fusion reactions to occur. So fusion reactions led to the formation of lighter elements. Specifically, you got hydrogen and helium formed. Little bit of lithium, a bit of deuterium, a little bit more of some other things that decayed over time. Um, but mostly you got hydrogen and helium. And so um, as we move on through time, you would see that nuclear fusion in stars will convert some of the hydrogen into helium. That only accounts for about 2% of the helium, maybe 3% of the helium that we have. The rest of it occurred in that early nucleosynthesis, the Big Bang nucleosynthesis. Um, in later in later stars and larger stars, and that's some of the stuff that we've looked at later on in class. You're going to have some other reactions occur. So you're going to have conversions of helium to carbon. You're going to have iron form. You're going to have silicon form. So you're going to have that very small percentage. So about 1% or so of the universe form through nuclear fusion that happens in stars. But the majority of the basic elements that we find throughout the entire universe, the hydrogen and the helium, that was all formed in those early moments of the Big Bang. So we know that all of these different places within the universe have a high concentration, almost 75%, it's about 74% hydrogen, about 25% helium, because we can look at the spectroscopic emissions or absorptions from distant stars and galaxies. And just like I showed you before, there's a particular signature. So even if that signature moves, you still know, okay, well, this is the pattern, even if it's moved slightly on or moved a great deal on the printouts, you can still tell what the composition of a star is by looking at that spectral readout. Um, so we've got about a 3-to-1 ratio of hydrogen to helium, and so is that is our big idea that there had to be something going on before just nucleosynthesis within stars. So something major had to happen, and the Big Bang accounts for that. So the observed 3-to-1 ratio of hydrogen to helium, along with the relative scarcity of heavier elements, yields critical clues about the density, temperature, and expansion rate of the early universe. So that is support for the ideas that we've talked about here. Correlations between the observations and predictions are striking pieces of evidence in support for the theory. So when we talk about hydrogen and helium, we can call those primordial or like the original atoms, essentially. They originated in the Big Bang, and they did not occur via nucleosynthesis in the stars. All right. So this is the list of guiding questions for this last part. So this has just been a summary of all the stuff that we have covered up to now. You should have the majority of this already at your disposal, and you are welcome to use this recording to just go back through and check and make sure that you have your answers in as you see fit. Remember, please, that your answer should be a good, solid paragraph. Maybe a couple of paragraphs, depends on how you want to arrange it, but that you are, let me go up here to the top. You are constructing an explanation. Okay, so this is more than just putting out a bullet point or two. This is actually constructing an explanation. So make sure you're doing a good job of that, and I'll see you in class.